Hi, my name is Ava Martino, and I'll be presenting on Lab 4, Physics 2211, Oscillations. In the introduction, I'll outline the purpose of the lab and introduce some key concepts used during the experiment. I will analyze the mass and springs motion from the video and create a computational model in GlowScript based on the tracker data we collect. Then I'll analyze the results. Finally, I'll address the questions what if and what does it mean. The purpose of this lab is to investigate the motion of a spring mass system, with the mass oscillating vertically on a spring while swinging in arcs. In this experiment, the system is the spring, while everything outside of the system, such as gravity and the earth, constitutes the surroundings. Before we observe the motion, it is good to note that the energy in the system will be zero. And for a quick preview of the results, the change in total energy is zero, and the real and computational models will appear similar. Some important concepts we use include the energy principle, which is the change in energy of a system is equal to the work on the system plus the exchange of thermal energy. You can see the equations for the energy principle on the right. Delta E is equal to W, and delta E is equal to delta K plus delta UG plus delta US. We also use Newton's second law, which states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Additionally, we utilize the position update and velocity update formulas, which you can see on the bottom. Here's a short segment of our tracker data of the mass and spring. If you examine the graphs on the right, you will see how x and y both follow a parabolic motion. So for the initial conditions, I changed the mass's mass to be about 0.402, and the initial position was 1.44 e to the negative 0.1 in the negative x direction, and 5.97 e to the negative 0.2 in the positive y direction, which we obtained from the tracker data. The initial velocity was set to 0, because the mass came from rest. Finally, we changed the time to 0 and delta t to 1 divided by 175. In GlowScript, L0 and Ks were given. I found the system energy by using the kinetic energy formula and potential energy formula. Then I added them together to find the total energy of the system. I then found the force of gravity and spring using the initial energies and added them together to find F net. Then I used the position and velocity update formula to find the new position and velocity of the mass. Finally, I found the changes in energy by subtracting the initial energy from the final energies, and found E by adding K, UG, and US, and delta E by adding delta K, delta UG, and delta S. Here is a result of the computational model. On the left, you can see the results from GlowScript, and the right you can see the results from Tracker. Both graphs have an oscillating motion, but the computational model is not as consistent as the tracker data model. This could have been caused by issues within the code or how the data was tracked. Now, what does it mean? Is the energy principle satisfied? Because there is no work being done by the surroundings on the system, or any energy coming out of the system into the surroundings, energy is conserved. So the energy principle is satisfied, meaning there is no loss or gain of energy within the system. This can be seen with the equation delta E of the system is equal to the work of the surroundings plus Q, which is thermal energy. For the second what does it mean question, we had to calculate two separate estimates of the oscillation periods, one from the x position and one from the y position. So I took an average from 3 different periods for both x and y. For the x position, the oscillation period was around 1.614, and for the y position, the oscillation period was around 1.487. So we can conclude that the period is different depending on the direction you choose, and that it is best to calculate the spring constant of both axes.